So this is a velocity time graph. As you can see here, the difference between the ones we've been doing is just the fact that we've got velocity as the y-axis instead of the displacement or the distance. Okay, and in this graph, we can start off below zero. We start off negative because we have a negative velocity. And negative velocities are interesting. Negative velocity means we are traveling backwards. If it's a motion in a straight line, we are traveling backwards down that straight line, opposite to the positive direction, at a velocity of -1. And here, we then reach a velocity of 0. So to go from A to B, we're going from a velocity of -1 to a velocity of 0. So while the graph is going up, it might be a little bit counterintuitive, but what's actually happening is we are slowing down. And a change in speed over time, well, that is an acceleration, or in this case, because we're slowing down, is a deceleration. In fact, what this means is this is still an acceleration. It's a positive acceleration because it's an acceleration in the positive direction. The effect of that acceleration is actually to slow us down because we had a negative velocity. So when acceleration is opposite to the velocity, what we have is a slowing down as a result of that acceleration. Okay, and our acceleration here, we've accelerated by, if this is -1, 0, 1, etc., and this is going 1 second, 2 seconds, 3 seconds, and this velocity is meters per second, the standard unit that we have, time in seconds, again standard units. Then we've decelerated by 1 meter per second in 1 second. So the acceleration here is 1 meter per second squared. And it's the gradient, isn't it? It's the gradient of that line. Just like in the next section, go from B to C, we have accelerated by 3 meters per second in the space of 2 seconds. So we've accelerated by 3 meters per second per 2 seconds. So it's 1.5 meters per second per second. So that 3 divided by that 2, 3/2 meters per second per second. The acceleration is 3/2 meters per second squared. So the gradient of a velocity time graph represents our acceleration. And that's really important. It's also really important to note what I was saying at the start of this video, that when we have a positive acceleration going from a negative velocity towards 0, it is still an acceleration, but the effect of the acceleration is to slow things down. Now, from C to D, in fact, we still have an acceleration. We call the whole thing acceleration. We have an acceleration at the same rate of acceleration that was in the positive direction. We end up with an acceleration that has a gradient, that's a gradient of -3/2 meters per second squared. So a negative acceleration, when we have a positive velocity, slows us down. But we continue to have a negative acceleration from D to E. Over the course of 2 seconds, we decelerate by 1 meter per second. So we have an acceleration of -0.5 meters per second squared. But because we're going from 0 to negative, that ends up actually speeding up this particle or whatever it is, because we're starting from a velocity of 0, and a negative acceleration from a velocity of 0 makes our velocity more negative, and therefore the magnitude of our velocity or our speed becomes greater, which is a really interesting point. At which point we have, from E to F, we have a flat section. Well, during that flat section, interestingly enough, what we're doing is we're maintaining a constant velocity. Okay, a constant velocity means that we're not staying still. That vehicle or particle or whatever it is moving at -1 meters per second. So a horizontal line on a velocity time graph just means a constant velocity not a constant distance or displacement. So if this was a distance time graph, E to F would be a constant straight line, a constant gradient on one of those graphs. Finally, F to G to H, all through there, well, I hope you can see that that is a constant acceleration. It's a constant acceleration of 1 meter per second squared. So F to H has an acceleration of 1 meter per second squared. However, you might want to split that up into two different sections, because from F to G, that acceleration is slowing us down, going from -1 meters per second as a velocity to 0 meters per second. And then from G to H, it is speeding us up. So it looks like it is split into two directions of motion, but the acceleration is constant throughout that. And I don't want us to use the term deceleration, because deceleration can get confusing. Positive acceleration is an acceleration towards the positive direction. Negative acceleration is an acceleration towards the negative direction. And in both cases, it can either slow us down or speed us up. Here, positive acceleration slows us down. Here, it speeds us up. Here, negative acceleration slows us down. Here, it speeds us up. Here, positive acceleration slows us down, and here, positive acceleration speeds us up. It's really an interesting thing to look at. It's also worth pointing out something interesting. Let's think about E to F. E to F is the easiest place to see this. Here we're traveling at -1 meters per second, and we travel at that velocity for 1 second. And if you think back to your GCSE maths, your distance is your speed times your time, right? So your distance from E to F, this section here, is going to be your speed, which is -1, times your time, which is 1 second overall. So the distance traveled here, actually, if we think about this -1 velocity as a speed of 1, here we have traveled 1 times 1 meter. So that there is 1 meter of travel. It's actually the area of that square, which means, in fact, we can find the distance traveled overall. It's just this distance was in the negative direction. So the distance here would be 1 meter. The displacement would be -1 meters. We'll do a similar thing here. This triangle here has a displacement of -1 meters, and this triangle has a displacement of -0.5 meter. So this here, we have 0.5 meter. From C to D, we have this triangle here, 3 times 2 divided by 2. That's going to be a positive distance and displacement of 3 meters. Here we have another 3 meters. And this section over here, we have another -0.5 meter, -0.5 meter displacement. So if we want, we can actually calculate the total distance and the total displacement. The total distance will be all the positives of these added up. So from A to B will be a 0.5 plus 3 plus 3 plus another 0.5 from D to E plus 1 from E to F plus a 0.5 from F to G plus a 0.5 from G to H. So you've got 3, 6, 7, 8, 9. So it's 9 meters distance traveled. However, the displacement would be a bit different. You have to take the negatives into consideration. So anything below the time axis is negative, isn't it? Because that's where we've got a negative velocity. So we'd have -0.5 plus 3 plus 3. Take away a 0.5. Take away 1. Take away a 0.5 plus a 0.5. So plus 0.5, take away a 0.5, they cancel. So -0.5 and -0.5 is -1. Take away another 1 is -2. So we have 3 plus 3 take away 2, which is 4 meters 4 meter displacement altogether, and 9 meters distance travelled altogether.